Hello and welcome to my presentation. I am Bahar Asgari from Georgia Tech. In this presentation, I introduced Meissa, a fast and scalable systolic array for matrix multiplication. Matrix multiplication is the key matrix algebra in several applications, such as in neural networks. For instance, to perform a convolution in neural networks, a common practice is to convert the convolution to a general matrix multiplication as shown in this slide.
Matrix multiplication has two main features. It consists of several similar operations and it captures a high data reuse rate. As a result, systolic arrays have been proposed as a fast and low-cost solution to perform matrix multiplication. In prior work, two types of systolic arrays have been proposed for matrix multiplication. The first type is non-stationary, which consists of Mach units. To perform a matrix multiplication, both of the operands flow through the array. To see how it works for multiplying matrix A and B, shown in this slide, I split the timeline into three phases. The first phase includes only the processing. At this phase, as the animation shows, the two operands are meeting each other at the Mach units, and once they both passed a Mach unit, an element of output is ready and stored in that Mach unit. For instance, the yellow element shown in this slide. The systolic array keeps doing it until it's time to offload the output from the Mach units, which takes n plus m time steps. After phase 1, we can start offloading the output elements, the first time step of which can be overlapped with phase 1. Then, in phase 3, we only offload, which takes n time steps in total. The second type of systolic arrays are stationary ones that are also made of Mach units. These are the more popular systolic architecture also used in Google's TPU. Here, one operand, for instance B, stays in the Mach units during the multiplication. So first, we need to load matrix B, which takes m-1 steps. While loading last row of B, we can start the process. Then, if we continue, we see that processing takes m-1 steps. Starting from next step, or in phase 4, the outputs are getting ready. Therefore, we see that the elements of output are pushed out. Phase 4 takes n plus p minus 2 time steps. And one last phase is required to read the last element. Till now, we saw that both types of systolic arrays proposed by prior work have a common challenge of scalability, which means that the latency of both of them increase linearly when any dimension of any operands increase, which is not the optimized latency. In fact, matrix multiplication consists of multiplications and additions, among which adding m numbers can be done in log m rather than m steps. Therefore, in an optimized design, latency should be able to increase sublinearly with the input size. To achieve this optimized design, we propose a new systolic architecture consisting of separate multiplier array and adder tree array. As a result, when any of the dimensions of the operands grows, our proposed systolic array is faster than the other two proposals. Let's see how. This is also a stationary systolic array. Therefore, we assume B stays in the multipliers. And first, we load B, which takes m-1 steps. Then, in phase 2, A starts to flow, but not in a diagonal form. In phase 3, while multiplications are going on, the output of each column of the multiplier array goes to an adder tree that are balanced and pipelined. We continue doing multiplication and addition in parallel. Then outputs start to get ready. In phase 4, multiplications are over and we only wait for additions to be done, which takes log m time steps.
This slide shows processing elements and the connections between them for the two MAC-based systolic arrays and Meissa. The processing elements of all three designs include two input registers R1 and R2 and an output register R3. Their differences are in where the adders are located and what data pass through and in which direction data flows. Besides, as this slide shows, for the stationary and Meissa, the submultiplications can be arranged such that sequential ones reuse a common stationary operand to save energy and the time of loading the operand. For the non-stationary, however, as the partial outputs are stored in the processing elements, for every submultiplication, both operands must be re-streamed into the array. This is one of the reasons that the non-stationary systolic arrays have been less frequently used. The other challenge of the non-stationary systolic arrays is that their performance depends on design choices, which limit their implementation and applications. This slide illustrates such a challenge by showing the time steps for processing layers of ResNet 50 along with the matrix dimensions for two different choices about how to push inputs into the systolic array and how to offload the output. As the figure suggests, depending on the matrix shape, one design choice could be better than other, which complicates the application of the non-stationary systolic arrays. For more details, please refer to the paper. Before going to experimental results, we thoroughly analyze the impact of scaling the input sizes on performance for the three systolic arrays by varying one dimension of the inputs at a time. As the diagrams in this slide show, when any dimension of the inputs grow, the number of time steps of Meissa is smaller than the other two systolic arrays.
To evaluate our proposed systolic array, we implemented on a ZYNQ FPGA using Vivado HLS. We used appropriate pragmas to describe the multiplier array as well as making sure the adder trees are balanced. Our benchmarks are 5 deep neural networks with various matrix sizes. We compare latency and energy consumption. Our evaluation results show that on average our proposed systolic array works 1.9 and 1.8 times faster than non-stationary and stationary systolic arrays respectively, while consuming approximately 2 times less energy.
To better explore the rationale behind the different energy and power consumption, this slide compares the breakdown of dynamic power consumption. Note that the static power consumption of all three designs is similar. As the diagram suggests, the lower power consumption of Meissa stems from less signal transmission for two reasons. First, during the matrix multiplication steps, the multipliers transfer data only in one direction. In fact, the connections in the other dimension are used only for loading the stationary operand. And second, the topology of the adder tree reduces the transmission of data across the processing elements.
In this presentation, we saw that systolic arrays have seen significant interest because of their unique interconnection that satisfies the unique requirement of data reuse in matrix multiplication. Although the systolic arrays in prior work offer high throughput, their latency is not optimized. To optimize latency, we propose a new systolic array consisting of separate multiplier and adder tree arrays, which works faster than prior proposals.